projects. In this video, we are going to explain about the project title EsaNet Environment Semantics Enabled Physical Layer Authentication. Before diving into the execution, let me give you an overview of the project. EsaNet, that is Environment Semantics Enabled Physical Layer Authentication, is a security system for wireless networks that verifies the identity of devices trying to connect by analyzing environmental factors like signal propagation. By comparing these factors to known patterns, EsaNet can determine if a device is legitimate or potentially malicious, adding an extra layer of protection against unauthorized access and security threats. Traditional methods of wireless network security, such as password authentication, encryption protocols, and firewalls, have limitations. These include vulnerabilities to brute force attacks, phishing, encryption exploits, and the inability to detect sophisticated threats. They also rely on centralized security measures, making them susceptible to single points of failure. The proposed system integrates various algorithms, notably YOLO V5 and VGGNet, to enhance security in wireless communication networks through object detection. YOLO V5 offered in different versions like YOLO V5S, YOLO V5X6, and YOLO V8 is primarily responsible for detecting objects within images. Meanwhile, VGGNet brings its effectiveness in recognizing patterns within images. By combining these algorithms, the system extracts features and identifies objects of interest within the dataset. The model's performance will be assessed using mean average precision MAP, precision, and recall score metrics. MAP measures overall accuracy, precision evaluates false positives, and recall assesses false negatives, providing comprehensive insights into the model's effectiveness in detecting objects within the dataset. The project's results will help make wireless networks safer for everyone who uses them, including people who manage the networks, make IoT devices, and use them. It will also help researchers learn more about how to make wireless communication more secure and understand images better. This means better protection for personal information, more trustworthy devices, and new ideas for making networks safer and more reliable for things like phones, cars, and cities. To implement this project, we need software and hardware requirements. Hardware requirements of the project are operating system of Windows, processor of Wi-Fi and above, RAM of 8 GB and above, hard disk of 25 GB and above. Software requirements of the project are application is Anaconda, primary language is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, database is SQLite 3, front-end technologies used in the project are HTML, CSS, JavaScript, and Bootstrap 4. Algorithms used. These are the algorithms which are built in the project. We have built these algorithms to compare the performance with different evaluation metrics. And here, the YOLO V8 outperformed the other models. So let me explain you what YOLO V8 is. The latest iteration, YOLO V8, offers higher accuracy and speed with advancements like mosaic data augmentation and anchor-free detection. It comes in different sizes to cater to different application needs and computing resources. It explores anchor-free detection for faster and more adaptable object localization. Now let us execute the project. To execute this project, first we need to open the code folder which contains the project source code files. So here, these are the datasets folder. So the first one is EsaNetEnvironment YOLO V5 dataset. Let us open this. So here the dataset is split into train and validation. In the train folder, we have the images and the labels. So in the images folder, we have the signal images, and all these images are used to train the YOLO v5 model. And here in the labels folder, we have the labels for the corresponding images. So let us open this label folder. So here the first label represents the class index, and these four labels are the coordinates of the bounding box. Let us close this. So here, this is the label for the image, this. So here, when the image or the object is detected, it will be detected by the bounding box. So for that bounding box, we will have the coordinates which are present in the labels folder. So here, these are the coordinates of the bounding box, and here this is the class index for that image. And here in the validation folder, again we are having the images folder as well as the labels folder. So in the images folder, we have the images of the signals which are used to evaluate the performance for the YOLO v5 model. And in the labels folder, we have the labels for the corresponding images. And here we have the README dataset and README.roboflow text documents. And this is the EsaNetEnvironment YOLO v8 dataset. And this dataset is split into train and validation. So here in the train folder, we are having the images as well as the labels for those images. So in the images folder, we have the images of the signals which are used to train the YOLO v8 model. And in the labels folder, we have the labels for the corresponding images which are present in the images folder. So here in the labels folder, we can see the first one is the class index, and these are the coordinates for the bounding box. Let us close this. And in the validation folder, again we are having the images folder as well as the labels folder. In the images folder, we have the images of the signals which are used to evaluate the performance. And in the labels folder, we have the labels for the corresponding images which are present in the images folder. So, and here, these are the text documents for readme.dataset and readme.roboflow. And this is the sample folder in which we have the test cases of the signal images which we will use during the execution in the front end. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It includes files like index.html, about.html, and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. And here, this is notebook.ibynb file. This is a Jupyter notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. Here, I'm copying the path. Now open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I'm typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address localhost, which is this, and port, which is this. Now copy this local link provided by the Flask framework. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flask framework. If we are a new user, we need to register first. So click on sign up button here. So here we need to enter all these details to register. But I have already registered. So click on login. So here we need to enter the username and the password which we have registered, which are static, and then click on login. We have logged in successfully and we are redirected to the prediction page. So here we can see a detection link, click on it. So in this project, we will do the detection for the signal images. So here we need to upload the signal images, and after uploading the images, the application will detect. So click on choose file. So from the sample test cases folder, I'm selecting this image. Now click on open. So here we can see that the image is loaded. Now click on upload button. So here we can see that the signal is detected with the bounding box. And here we can see the probability score, which tells us the confidence level of the detection. Now let us upload some more images. Click on detection link here. Click on choose file. So again, from the test cases, I'm selecting this image. Click on open. So here we can see that the image is loaded. Now click on upload button. So here we can see that the signal is detected with a blue color bounding box, and here we can see the probability score, which tells us the confidence level for the detection. Let us upload some more images. So again, from the test cases, I'm selecting this image. So here we can see that the image is loaded. Now click on upload button. So here we can see that the signal is detected with a blue color bounding box, and on top of the bounding box we can see the probability score, which tells us the confidence level for the detection. Let us upload some more images. Click on detection link here. Click on choose file. Now let us upload the images from the train dataset. So here this is the image which I have selected. Click on open. Now click on upload button. So here we can see that the signal is detected with the blue color bounding box, and here we can see on top of the bounding box the probability score, which tells us the confidence level for the detection. Let us upload some more images. Click on choose file. Now let us upload the image from the validation. So this is the image which I have selected. Now click on open. So here we can see that the image is loaded. Now click on upload button. So here we can see that the signals are detected. So here we can see multiple signals are detected, and we can see on top of those bounding box the probability score, which tells us the confidence level for the detection. Let us upload some more images. Click on detection link. Now let us upload the images from the YOLO V8 dataset from the train images. So this is the image which I have selected. Click on open. Now click on upload button. So here we can see that the signal is detected
with the blue color bounding box, and on top we can see the probability score, which tells us the confidence level. So in this way, by uploading these signal images, the signal will be detected, and we can see the probability score, which tells us the confidence level for the detection. Now click on graph link here. So here we have the precision and recall graph of YOLO. So here on the x-axis we have the recall score, and on the y-axis we have the precision score. And here we can see that this blue color line represents all classes. And here we have the FN score graph of YOLO, FN confidence graph, FN confidence curve graph. On the x-axis we have the confidence score, and on the y-axis we have the FN score. And here this is the confusion matrix of YOLO. And this is the precision comparison graph, and this is the recall comparison graph, and this is the MAP comparison graph. On the x-axis we have the score for the evaluation metrics, MAP, recall, and precision, and on the y-axis we have the algorithm name. Now click on sign out button here. The project aims to enhance wireless network security by combining wireless security and computer vision techniques through EsaNet. By employing advanced object detection algorithms like YOLO V5, YOLO V8, and VGGNet, the system adds an extra layer of protection to networks, benefiting various stakeholders.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.